Okay. Okay, so let's start. My name is Luis Crespo. My ID is lcrespo_m. If you want to contact me, it's the same ID in Gmail, Twitter, GitHub. So I'm going to talk about genetic algorithms. We'll have a quick introduction to the different types of artificial intelligence. Then I'll explain what are those genetic algorithms, what kind of problems they can be used for solving which kind of problems. And finally, I'll make a demo of a web application that uses this technique for solving a special kind of problem. Okay. Okay, so artificial intelligence is getting a lot of attention recently. Why is that so? Well, we'll see, but before that, we have to understand the different types of artificial intelligence. There's weak artificial intelligence and strong artificial intelligence. So the typical example of, oh, too bad. Typical example of weak artificial intelligence is, thank you, yeah, is chess, right? So 20 years ago, a computer was able to defeat the best human player of chess. We can see here Garry Kasparov being defeated. And how did the program play chess? Well, quite simple. It computed all the possible moves of the next turn and the next turn and the next turn. So that's a lot of different possible combinations, but there's enough computer power for that. There was enough like 20 years ago. And that's not really thinking, that's not really intelligent, it's just brute force, right? So that's why it's called weak artificial intelligence, because when you look at how it's done, it's just computing power, right? So every time we have a problem that we thought that required intelligence to solve it, and we solve it by computation power using traditional algorithms, well, it's no longer considered to require intelligence. And that's the limitation of weak artificial intelligence somehow, right? If we don't care that the computer is thinking, if it is intelligent or not, but solves the problem, that's good enough already. But we have also strong artificial intelligence. And in this case, the techniques are more complex, are more advanced. And it usually tries to imitate nature. And the most typical example is neural networks, where well, the program is going to model neurons and synapses, and then there is a real learning process where the neural network is exposed to some examples, then it will learn from them, and then when you present a problem that it hasn't seen before, it's able to respond from what it has learned before, right? And so just 1 year ago, a computer using neural networks was able to defeat one of the best human players of Go, which is a game that's not as easy as chess to win by brute force, because the board is much bigger. There's many more moves. So it's impossible to have so much computation power as to win by just computing all possible moves. There are too many, right? So this neural network was exposed to human games of Go. And after it learned, they made it play against itself. And it learned from itself. And then that way it learned strategies which were never imagined by a human. So that's why I want to show you a video. OK, there it is. So the computer has just made the move, and the player is now like thinking, like, what is this? Like, his face is I didn't expect that move. It's like, oh, now I understand. Oh, wow. Oh. And then he thinks, what I'm going to do now, I don't know how I'm going to, what's the next move? And in a few seconds, thinking, oh, I've lost. You see, right? So pretty amazing. OK. OK, so I was asking in the beginning, why is it that artificial intelligence is getting so much interest now by big companies, et cetera? Well, because in the past, like 10 years ago, making a big neural network, especially deep neural networks with many neuron layers, making it learn was very hard. It took like months to make a neural network, a big one, learn. Then some guys discovered a technique that made that easier, just from months to days. And also we have, of course, much more computing power. Now we have, for example, we can use graphic accelerators for computing in parallel so that you can propagate the signal through the network, et cetera. So that's why we can do things now that we couldn't do 10 years ago, like very good image recognition or winning Go. Anyway, after this introduction, I want to talk about genetic algorithms. They also imitate nature. They don't imitate the thinking process. So you see, in the strong AI, the computer is really thinking because we have neurons, we have synapses. It's simulating the process of a real brain. So we can really say it's thinking in a very simple way because it's a very simplified way of, or simplified model of a brain, but it's already thinking. Right? Here we are going to imitate nature by imitating evolution as a way to gradually get better and better results. So let's quickly review how natural evolution works. We have a population of living beings, and every living being is built from a set of instructions that is just a sequence of genes. And the ones that adapt better to the environment, they can survive and they can have children, and those children will inherit the characteristics. And there is also some diversity that helps make possibly slightly better children and slightly worse children. And you combine that together, and generation after generation, you are going to have better and better adapt beings. Right? The typical case is, well, the zebra, right? So the slower zebras, they are eaten by lions. They cannot have children. They die before they have children. The faster ones, they have children. And those children will be slightly faster than the previous generation. And you do that generation over generation, thousands of years, and you get faster and faster zebras, and of course, faster and faster lions, which have to eat zebras. OK. So we try to do the same thing for finding a solution that we couldn't solve by brute force. OK. So every individual of the population is a potential solution, and the environment is the problem we want to solve. We'll see how we do that. But how this works, we start with a random set of solutions, just very ugly monsters that adapt very badly to the environment. And we select the best ones, and we marry them to have children, or, well, we just let them have children, right? The best solutions have more children than the worst. The worst also have children because it's good to have diversity, but they have fewer. And we iterate over and over, and every generation we're going to have more better solutions than in the previous one. OK. At any moment in time we are in a given generation, the solution to the problem is the best of the individuals in this generation. So we keep iterating until we decide our solution is good enough, or we find, the user can decide when to stop, or there has been like 10 minutes without any new solution or whatever. So what kind of problems can be solved with this technique? Pretty much anything that we can encode as a sequence. The genetic information is a sequence, so we can encode it in a sequence. It can be numbers, characters, it can be symbols, whatever. And we need to be able to encode it, and we also need to have a way to evaluate which solution is better and which is worse, right? So we need to give a scoring. So for example, this is still a little abstract, but we have 3 solutions, which are just 3 sequences of numbers. We apply the evaluation function, and we give different scores. So this is like a lottery. When we want them to have children, this one has more tickets to the lottery, and this one has less tickets. So this one will be 3 times more likely to have children than this one, or 3 times more children, right? Every generation, we do the same. OK, so this is a very abstract problem. Let's see an example. A specific example is the Traveling Salesman Problem, which is a very typical problem. We have a list of cities, and we want to find the shortest route. So this is a very famous problem because it's kind of academic problem for computation, for techniques of finding solutions, but also because it is equivalent to other problems which are more useful, like logistics. We have big e-commerce with a lot of trucks. We want to give, for Christmas, we want to give all the deliveries, right? What is the best distribution of loads, of things to put in trucks? Where should each truck go? It's a matter of recombining different possible solutions in a sequence, and right? Planning, so we have a set of tasks and people that need to do tasks, and which is the best way to do that. Same thing. And this is only an example. There are many other problems that can be solved with genetic algorithms. OK. So again, why do we need genetic algorithms instead of just other techniques? Well, because when you have a lot of cities, the complexity, the number of possible permutations is huge, right? It's n factorial, and you say you take the first city, you have n possible choices. Second city, n minus 1 possible choices because one is taken, and so on, right? And this is huge. I mean, with only 20 cities, you have 1 trillion possible combinations. And 59 cities, you have about the same amount of possible combinations as atoms there are in the universe. So this is astronomical amount, right? I did a little measurement in my computer, and with 26 cities, with the power of my computer, it would take longer than the age of the universe to compute all possible permutations. So OK, my machine could be faster. Maybe there are machines that are 1,000 faster. Just add a couple more cities, already back to the same amount of time required. So the good thing about genetic algorithms is that it scales very well. You can add hundreds, you can throw hundreds and hundreds of cities, and it will quite quickly find a reasonable solution. It's not going to be the best possible solution, or we don't know, we cannot know if it's the best possible solution. But in a reasonable amount of time, we're going to have a pretty good one. And we can wait and see if we get better ones over the generations. OK, so how we do this, specifically how we solve Traveling Salesman Problem with genetic algorithms. So as we say before, we said we need a way to encode. So that's very easy. Every city is a number. How we do the evaluation function, we just compute the distance. That's it. For every sequence of cities, we compute the distance. The shortest roots are going to be better, and the longest ones are going to be worse. So it's the opposite of the other example, but anyway, right? We can do that. OK, and then how we make children. So we have a sequence of cities, which is the parent, and a sequence of cities, which is the father and the mother, right? So we can take the first half from the mother and the second half from the father, and we stick them together, but we have to skip the repetitions, right? So 5 to 3, and then 5 to 3 here. 5, no, is taken. 4, yes. 6, we go back here, and 1. Pretty simple. That's a simplification. We can add randomness. We can cut not just in the middle. We can cut somewhere else. We can add mutations, like we can flip some numbers, etc. But in the end, you make children by just combining the sequences of 2 elements of the population. OK. So, well, because this is supposed to be about JavaScript and web. Oops, this is, come on, wake up. OK. So I'm going to show a demo of a program. This is a static web program, 100% client side. There's no server side. So everything, all the computations are done in the browser. Right, so we have, here we can parameterize, that's the number of cities, that's the more important one. Also the amount of solutions per generation. And there are other parameters which I can explain later if you're interested. Right, so here we're going to see the map. Let's start. 200 cities is quite a lot. And you can see that very quickly, it starts to show you a very reasonable solution. When you have lines crossing, this is a room for improvement, right? Boom, there, it uncrossed, right? So you can see how quickly we get to a reasonable solution just by looking at it in a few seconds. And we can see we have 6,000 generations per second, not bad. Let's try again. Let's put twice as many cities. See how it behaves. Takes a little longer to, you see there's a lot of crossing lines. And this one is very, oh, wow, that's impressive. There's a knot here. Oh, this is very fun to do. It's like I can spend a long time just looking at how it solves. OK, one more interesting thing is our computers, they have multiple cores, right? So what I'm doing here, by the way, is the UI is managed by some JavaScript code, but the computation is not managed by the UI, because if I put both together, the UI would freeze, right? You probably have seen that. You cannot do long computations, because then the UI doesn't refresh. So what we are using here is web worker that does all the generations, all the genetic algorithm is in a web worker, and the UI just is totally independent thread. So we're going to take advantage of this. I'm going to put, in the parallelism, I'm going to put 4 web workers. And then every web worker is going to be a different population that is going to evolve a solution independently. What I'm going to show here is the best solution of all the populations, right? And also every 10,000 generations, I'm going to share the best solution with all the populations, with all the workers. So let's see. You can see we have more generations per second than before, like 4 times more. And well, if you measure it, it's going to be also, the distance is going to be shorter than if you have a single worker. We can see a histogram here, which is every second there's going to be a well, a bar. If there is a solution, it will show as a bar here. If there is no better solution than before, it's just blank. So we can look at it and see when it's not changing, then it's time to stop. But you never know, because sometimes we have like there's a little change that triggers a lot of evolution also. Anyway, this is pretty much what I wanted to show. And if we click here, we go to, this of course is in GitHub. So you can go to github.com/elcrespo, and you can see the source code. It's JavaScript, it's TypeScript, and you can play with it, of course. Just let me know if you do something. OK.